Hello, thank you for joining us. All right, I've gotten the thumbs up. So hello, and welcome back to Astronomy at Home. We've missed you. We hope you've missed us. We're brought to you as always by the DiRAC Institute and Astronomy on Tap Seattle. And we're so glad you could join us on this snowy evening in Seattle for another night of fantastic science. We have a great talk coming up for you, but before we start, some of the usual reminders. We'll have our Q&A session with the speaker immediately following the talk. So feel free to add questions along the way, either in the Zoom chat or the YouTube chat if you're following along there. We will be having our usual Instagram Live interview tonight after the talk at 8 p.m. So make sure to get your questions in during our Q&A. Okay, let's get started. So we have a great guest for you tonight. He is a research scientist at the University of Washington working with the Rubin Observatory and is also the technical lead of the Alert Production Group for the Legacy Survey of Space and Time. Please give a very warm welcome to Dr. Ian Sullivan.
Hello, Nicole. Thank you very much for that warm welcome. Why don't I get my screen shared so you can see what I'm talking about. All right, should be able to see my first slide now. All right, so I'm going to tell you a little bit today about the Rubin Observatory and the survey, the 10-year survey that we'll be conducting with it called the Legacy Survey of Space and Time. And with the new hardware improvements and the large sizes of this telescope, we've also starting to have to deal with some new technical challenges. And I'll tell you a bit about one of those challenges, our solution to it, and how that solution actually enables us to extract some new science out of the data. And what I'm showing here is, because I love the picture, these are the mountain ranges of Cerro Picon, where the Rubin Observatory is. That's not actually the Rubin Observatory in the distance. That is a different observatory on a nearby mountain, but they got a nice shot of a rainbow just right above the observatory. So what is the Rubin Observatory? The Rubin Observatory is under construction, seen here in 2018, I believe, in the mountains of Chile on Cerro Picon, and located about 100 kilometers from La Serena in Chile. You may be more familiar with the city of Santiago, and that is a few hundred miles to the south. But the observatory we're currently building, most of the main building is currently complete, and we're just finishing the dome, though all of that, like everything, has been slowed a bit by COVID. However, you can see that all of that is coming together, and right now is the peak building season because down in Chile, in the southern hemisphere, we are now in the summer. And one final view of the observatory looking out over the mountain range in the distance. This is taken from a drone. So, more about the Rubin Observatory and what we do with it. So, the heart of the Rubin Observatory is its camera. And this camera is not like most cameras you'd be familiar with. The physical camera is about the size of a small car. And with 189 CCDs, each with 4,000 by 4,000 pixels, that if you actually tried to display that entire image at once, it would take over 1,500 HD TVs to display the entire thing all at once. So these are really big pictures. So the camera is going to be taking over 20 terabytes of data every night for 10 years. That's a lot of data. Here we can see a rendering of the camera itself. We have 5 different filters that can be fitted at a time, and they can rotate through inside the cryostat. Each filter essentially defines a wavelength range, blue, green, red, that the picture will be when it's taken. And because it's inside the cryostat, that means that we can quickly change between those filters. we'll actually observe in a total of 6 different filters, but we can only fit in 5 within the cryostat at a time. So each night is going to be limited to a total of 5 different filters, and we'll have to change that out in between nights. The camera itself is actually built. We have the full CCD, set of CCDs assembled. This is being done in Slack, and you can see them installing the rafts of 9 CCDs each into the actual hardware. And the neat thing about this is that we can actually take some initial images with it. So this image is one I like. So this is just taking that massive camera and not with any of the lenses, no mirrors, just as a pinhole camera, and taking an image of a photograph of Vera Rubin, who the observatory is named after. What is a little hard to appreciate from this picture is just how large this is. So let's zoom in. So you can zoom in and begin to see each of the individual CCDs a little bit further, and zoom in further, and you can begin to see some of the things of the, you can see some little imperfections in these CCDs because this is just a quick test setup and not the actual official, in place and the full cryostat, so not as perfect of optics. And we can keep zooming in, and we can keep zooming in. And this is about as far as you can go with here, but you can see tiny individual pixels, which if this was enlarged, it would be enormous. It'd be well beyond the size of your room by now. So we have these large images. What are we going to do with them? Past surveys, like the Sloan Digital Sky Survey, have observed a lot of the sky, and they've made massive amounts of science from them. Other surveys are able to observe in high resolution, high detail, small parts of the sky. Now, what's unique about the Rubin Observatory and the legacy survey of space and time that we conduct with it is that it's going to allow us to observe a lot of the sky at some of the highest resolution that we can observe from the ground. So the image on the left is the image from the Sloan Digital Sky Survey, and on the right, this is not from LSST because LSST is not fully built, the Rubin Observatory is not fully built yet, but it is taken with a comparable camera, the Hypersuprime cam. This telescope, however, does not have the same field of view, cannot observe the same amount of sky, but it can observe it to the same level of detail. So this is the kind of image that we can expect to get with the Rubin Observatory. And the improvement over our past images is astounding. There are things we cannot see at all that are now apparent in the LSST depth image. We can see all kinds of detail about these galaxies. We get much more detail about the colors of our objects after we observe them with different filters. And because it's such a large area observed and at such high detail, the LSST will record far more stars and galaxies than have ever been recorded before. Now, we expect 37 billion by the end of a 10-year survey. In addition, we expect to detect and fit the orbits for an additional 6 million asteroids. This is approximately 10 times more than we have orbits for today. This will fill out our understanding of our galaxy, of our solar system, and hopefully a lot of the rest of the universe. This ties into the key science themes of the LSST survey. Beginning from the largest scale, we want to understand what is dark matter and dark energy, and we can get at this with LSST because we have such a large amount of sky observed in such detail. We can measure very precise oddities in the shapes of distant galaxies, and through a lot of mathematics, work out what details of weak lensing, that is, intricate details of gravity at large scales. And that can tell us more about things like dark energy. On closer at home, at the Milky Way, we'll be able to observe far more stars within the Milky Way than have ever been seen before, simply because we can see things that are fainter. We'll be seeing more of the sky. There's going to be more stars that we get to see. Going deeper into the solar system, with our new catalogs of the asteroids, this is going to allow us to monitor for potentially hazardous asteroids. So by expanding the number of asteroids that we have the orbits for by a factor of 10, we'll have much more knowledge of any orbits that might potentially intersect with the Earth in the future, signaling something that it would be an asteroid we would want to watch out for. And the longer we have to prepare for something like that, the better a chance we have to actually do something about it, maybe correct the course of that asteroid. And just find out more about the asteroids in our solar system. Millions of them, and there's all sorts of classes of them. There's the main belt, which we know the most about, but there's distant ones out around Neptune, and particular clouds and resonant orbits with Jupiter. And we can even start to detect objects out in the Kuiper belt, objects like Pluto, a potential planet 9, or 10, depending on which ones you're counting, and just find out a lot more about the solar system and the neighborhood around Earth. And finally, in addition to all of this, we want to be able to find the things that go bump in the night. All of the small objects that change, a supernova that goes off in a far distant galaxy. With LSST surveying so much of the sky in so much detail, we'll see lots of supernova. I'm not even going to put a number down to it. And be able to measure variable stars and all the things that are changing throughout the universe. So LSST is going to open up a lot of science. This gets to where we come into the problems. So, problem that I was going to tell you about today goes by the wordy name of differential chromatic refraction. What this is that anytime you're familiar with light, when it goes into a water glass, you see the straw bend. So this happens anytime light goes into a new medium. Now, water is denser than air, so it bends. Similarly, when the light from space enters our atmosphere, that's not the atmosphere isn't as thick as water, obviously, but it is still thicker than space. And so light bends. In this cartoon here, we can see the blue star on the edge. That's the true location of a source. And as it comes through space, that is going straight, and as it enters the atmosphere, it gets bent. And it's always bent so that when we observe it, it looks as though it is closer to zenith than it truly is. Zenith is the point directly overhead. Something that's coming directly overhead will not appear to bend at all. This is like if you're looking straight down into that water glass. You don't see things bending sideways, not directly down. Overall, this is something astronomers know about. We've been correcting for this for decades. But it gets problematic once we have differences in the amount of bending between, they say, the red and blue light within the same image. Now, I was describing those filters earlier that restrict the image that we're taking to, say, a blue image or a red image. But we're not expecting lasers from space. So we don't filter everything but one single wavelength. It accepts a range of wavelengths. In the case of, say, a relatively blue filter, call it G band, one of the astronomer names, that accepts light from about 400 nanometers out to 550 nanometers. And within that range, the bluer end of the light that's accepted through the filter is bent more towards zenith than the redder light. So what that means is that a star in our galaxy, the light coming from that star is going to get smeared out, and the bluer light will be smeared more towards zenith than the redder light. The problem with this is that each star has a different spectrum. Every single star, it will emit different amounts of blue versus red light and everything in between. And we don't know what that is in advance. So every star is going to have its shift applied differently. There are things that can be done to fix this. Amateur astronomers in the audience may have heard about an ADC, an atmospheric dispersion corrector. So this is a device where you have two prisms, as you can see on the right, and you can change their spacing. And the prisms undo this effect of the atmosphere, because if you know how much atmosphere you're looking through and at what angle, you can simply adjust your prisms in order to correctly unsmear that light. And this is a great solution, but you can't always build one in. In particular, the Rubin Observatory does not have one. We have a 8.5 meter diameter main mirror. It's 27 feet, and the camera is about 5 feet across. No one has ever built an ADC that could be 5 feet across, and there isn't space among the optics. I mean, the mirrors, if you tried to fit it in there, it would block the light. So we don't have one. That means the light gets mixed and is recorded on the CCDs, and once it's been measured, mixed, you can't unmix it. So what do we do about that? And what does that look like? This is an example of images that are about at the resolution that we expect to take with LSST. And on the left, we have a science image. And on the right, we get the result if you subtract a template from just 2 hours earlier in the night. And over those 2 hours, it's picked up a little bit more air mass, astronomers call that, where as you look further away from zenith, you're looking through more and more of the air, and so astronomers just call that air mass. There's we have a simple expression from it, but what matters now, right, is that a larger number means that there's more differential chromatic refraction. It becomes a bigger effect. And these two images did not have the same air mass. And so we're not able to subtract them properly. You can see on the image on the right, where the stars are, we have these ugly little blips of white and black. That means we're over subtracting, that's the black, and then next to it, under subtracting, that's the white. And there's things you can do about this. You can do machine learning and train up a computer so that it knows that things that look like that are to be ignored. But the problem then is that you miss real things. Like if an object moves, you would also see an effect like this. So then you can't tell, is the thing moving? This is not going to be a problem for stars because they don't usually move on us, at least not much. But asteroids move quite a bit, and we want to be able to measure them, measure their speeds, get their orbits, and measure their brightnesses accurately. So this is something we have to fix. So how do we go about that? Over here, I've got a cartoon of how that gets modeled. At the very top, we have our smeared out image. But in this, which is going over the full band, in the little shaded figure to the left, you can it's showing the wavelength profile of this G band that I was talking about before, going from 400 to 550 nanometers, or in angstroms, 4,000 to 5,500. And over that full range, there's smearing. So let's pretend that in half of the range, there's no smearing, and in the other half, there's also no smearing, but the two are shifted relative to each other. So those are the two lower cartoons here, where you can see that within each subband, everything is symmetric. It looks circular, and one is shifted up and one is shifted down. And it's only when they're combined, because the real image is the entire band, when you add the two together, you get your smeared out image. So this is a convenient way of thinking about it, but we still only have measured our smeared out image. If we had these subband images, then, well, we would have a different telescope, because we would be using different filters. But then to get those different filters, we'd have to take twice as many measurements because we would have more filters. So we can't quite do that. Also, as the text says here, no, this is an approximation. Obviously, within these two subbands, it's still going to be some amount of smearing. But as you make more and more subbands, the approximation gets better and better. But the way that we can solve this is that we don't have just one image. We'll take many images, and each one is going to be smeared out differently. And if taking the knowledge that the sky itself is mostly not changing, and that this smearing comes from the atmosphere, and the smearing is, we have formula for how much smearing we should expect, even within each of these subbands. That means we know how much each one should shift and in which direction. And if we assume that within each subband, the real sky is not changing at all, and that all that's changing is the direction and the magnitude, which we know, then this means that this is a problem we can solve. I'm going to throw some math at you. So in the middle here, we've got our images. These are the elongated images, which I'm calling S. And our model has these Greek letters, alpha and beta. Each shift, which we mathematically know because we know where the telescope is pointing, is something that we're applying to our subband images, which should reconstruct all of the actual images we observed. This still isn't helping us because all we have is the actual images, and this is a very complicated solution because there's a lot of pixels in the image. This shift is shifting everything all over the place. It's not something you can directly solve. So how do we get around that? We can rewrite everything so that we're solving for just a single subband with shifting back and forth all of the other subbands except for that same one. This seems like a bit of a kludge, but it works because we can get a guess at one subband and then go and make a guess for all of the other subbands. And then we can take those guesses and feed it into the next iteration. And then we can keep iterating through and watch as our solutions hopefully finally converge to images that are now at our subband resolution. So this is at a finer frequency resolution than we actually were able to take with our camera, finer than the filters. How does that work? Now shows some examples here. These are all simulations, so I knew what was going into them. On the top is what you get if you just naively do what we would normally do and subtract off the best template that you could make from the science image. And you can see that you get some kind of nasty, here it's red and blue, positive and negative. And if you look closely, you can see because these are actually these are different stars where the stellar spectra is accurate within these stars. You can see that they don't all have the same patterns. Like in some cases, the red is on top and the blue is on the bottom, and other cases, the blue is on top and the red is on the bottom. So that means, it's not just a single shift or some sort of, the difference in what the camera saw. The actual light from these different stars has been mixed and smeared out in different ways, and you can't undo that. However, in the bottom row of images, where we've built up a model of the subbands and then use those to shift the subbands and subtract them off from our science images, it's not perfect yet, but we're doing a lot better. So that looks very promising. And this is where we start getting some ideas, like, well, now, because this started out as just wanting to be able to make better image subtraction so that we would be able to detect things that were changing in our images. But now we have images, instead of 400 to 550 nanometers, we have 400 to 450, and 450 to 500, and 500 to 550. This is 3 times as much information as we had before. And maybe we can do something about it. Maybe we can actually get colors from our images. Since these are all simulations, I know exactly what went into them. So here's some examples that I pulled out of the spectra of different stars. Now, there's a lot of data here. What I just want you to pay attention to is that in some of them, and what's listed here are different types of stars, and in parentheses is their temperature, which is in Kelvin. But these are these are so hot. You can think of Kelvin as Celsius because it really doesn't matter very much at those high temperatures. In any case, these are stars are hot. Our own sun is a type G star, so right there, upper middle. That's not our sun, by the way, but it's like that. What we can see is that the red points, which is what we've actually measured from these subbands, is closely following the real spectra that went into them. And we can tell the difference between a cool star, like a type K star, and a really hot star, one of these type A or type B stars. We really can see that the different stars are being measured differently. We can really see the difference between the redder star and the bluer star. What's more, we can see objects that are more interesting. So quasars are distant black holes that as the black hole accretes matter, it warps space around it, and the matter spiraling into the black hole is heating up so hot that it's glowing incredibly bright. But because the black hole is warping space to such a degree that it focuses all of that heat in a single blast of light straight out from it. Obviously, this is a very dramatic thing. So we see these in distances we measure in redshifts. And a redshift is think of it in a measure of a fraction of the history of the universe. So a redshift of 1 is approximately half of the half of the time light would take from the beginning of the universe till now away. These are very distant things. We've seen quasar out to redshift of 9. But these quasars have spectra that look very different from the spectra of stars. And we want to be able to detect these because these are our insights into black holes, that they're very fascinating things to look at. And what we can see is that the quasars have interesting features in their spectra, and we can kind of even start to tease out some of those features from these subbands. Certainly with more data and finer subbands, you probably could. This is where we get to, the final bit. It's like, well, okay, we've done all of this, and we've got these spectrums. Now let's turn this onto some real data, see what we can actually get out of it. So this is taking actual data from a precursor to the LSST called the Dark Energy Camera, or DCAM for short, and this is all from a single band. So normally this would be a grayscale image, but because we have observed at these different air masses and done our iterative forward modeling to build up our subbands, we can actually eke out color information. And around some of the brighter objects, you can see there's some obvious artifacts, things that we have to worry about, but there are some real color differences with them. The spiral galaxies have more of a reddish tinge, and if you look closely, you can even see that the spiral arms of them are a little bit more bluish than some of the rest of it. And what's more, this image I chose because it contains several of those quasars that I was just talking about. And those quasars we'd expect to be much bluer than the surrounding stars, because they have these features that are at high energy, which is more blue. And indeed, when we look at that, we can actually see, these quasars that we see in there, they are in fact some of the bluest things in the image. And this is just the beginning. So we can start to pull out all of this new color out of what started out as simply a way to improve our image subtractions because of these atmospheric effects, which is a rather nice tool to be able to have. And I'm looking forward to all of the science that we can eventually extract from these new color images within ranges that before we thought we could only have black and white. And that's where I'll leave it today. I think we are closing in on the right amount of time as well. So if I could turn this back to Nicole.
Absolutely. Thank you so much for that talk. And I'm sure everyone at home is clapping, but I'm gonna just clap for everyone. And while I'm waiting to get any questions that we have in the chat, I have one of my own. So I am particularly interested in the kind of latter part of your talk with when you started talking about quasar, because yes. I'm interested in studying the CGM, and really one of the only ways that we can do that is using quasar spectroscopy, so studying the absorption of light by gas of the light in quasars. And so I'm wondering if, I don't know, the using this method, which allows us to kind of more accurately get those values of the real measurement of that light, can you speak to how that might affect quasar spectroscopy or even measurements of emission in that kind of way?
Well, so there's two the sorts of targeted missions to really measure quasars go about this differently than LSST would, obviously, where they will actually put this is describing it for everyone else, where we take a prism and split the light so that we can measure all of the wavelengths, red to blue, and well beyond what the human eye can see. And then we can measure very carefully all of that spectrum. And something like that is going to do a far greater job of measuring quasars than this ever could. But what this allows us to do is that that targeted spectroscopy has to be pointed really precisely at a known quasar. You have to point it exactly where you want it to be. Whereas this is going to cover 18,000 square degrees, and so you can discover lots of quasars, and you'll have lots of quasar candidates from various, from comparing between the different bands that we already take, but there's the additional leverage now of within some of those bands that you'll have then a finer spectrum, say within the G band that I was showing pictures from, as opposed to a single point, you'll have, say, 3. And that is enough to find those objects that are interesting that a dedicated spectroscopy observation can go and follow up.
Very cool. So this will really kind of open up the universe to more quasar spectroscopic surveys.
Absolutely. Yeah, because LSST is observing so much. I mean, so many galaxies, so many stars across so much of the sky. It's going to be hard to wrap our heads around just how many objects we'll be detecting with that. And so the greater leverage that we have to identify those objects without having to have a human in the loop to go through and mathematically carefully work out which one is interesting or not, will allow us to get to those interesting objects faster.
Very cool. Thank you for answering my question. Meredith, I think we have some questions from the YouTube.
Yeah, we sure do. Thanks for a very fun talk, Ian. So full disclosure, one of these questions is from an astronomy colleague of ours. Ethan asks, he knows that quasars, those active galaxy things, and white dwarfs, which are like tiny little stars, have similar colors when you just look at the color naively and like don't know that you're looking at a star or a quasar. But could the extra color sensitivity from the technique distinguish a white dwarf from a quasar?
Well, actually, I hope so, yes, because one of the features of a quasar is that they have very sharply peaked spectra. Let's go back to that in here. Looking at these quasars, you can see that, so bear in mind, so each of these spectra I'm showing is rounded off on the edges because I have multiplied it by the actual, the filter that LSST is using. So it falls off on the left and off on the right because we will not measure anything there. So these are fairly smooth. You can see some small little dips in them, but when you compare that to the quasar spectra, they have these very tall, sharp spikes. So the finer resolution you have, the better a shot you have at identifying these sharp peaks. And that would differentiate between a quasar or a white dwarf or something else.
Awesome, thank you. We do have one other question from YouTube, and this one makes me smile because I will send this person a link to the talk that I gave a little while ago of astronomy at home. But Glenn asks, what is the impact of satellite constellations such as Starlink? And if I can be more specific, I'd be curious to know if you expect the colored stuff to, like, I hadn't thought about this before, even though I think about satellites a lot. Like, would you expect differential chromatic refraction to affect satellite trails?
So I think all we can really do with that is, if there is a satellite in it, that's going to be messing everything up, and we just have to, mask out. So that means identify which pixels are contaminated by the satellite trail. And we can't use those at all because the fundamental assumption of this technique is that the real sky is not changing, and that the changes we see are due to the different amounts of atmosphere that we're looking through. And if that's not true, if there's actually something really changing there, like a satellite passing through, even if it's fairly faint, then that's going to mess it up. So unfortunately, yes, satellites like Starlink are going to remain a challenge for this because they are fundamentally not in the equations. because they're up there in the real sky. It's not they're not affecting the atmosphere, though I guess we should be grateful for that.
Fair enough. Thanks, Ian. No more questions from YouTube. Nicole, do you have anything else to throw at Ian?
No, I think that we're at the perfect place to wrap up. Thank you again, everyone. Dr. Ian Sullivan here from the University of Washington. Thank you so much for your talk. And again, please join us at 8 p.m. where we'll be on Instagram. I'll put the handle in the chat or in the YouTube chat, and join us for our Instagram live interview at 8 p.m. And thank you all for joining us, and thank you again, Ian.
Thank you very much, Nicole. Thank you, Meredith, for helping take the questions. And thank you, everyone, for coming. Have a nice night, and I'd be happy to chat with you about whatever it is you want to on Instagram at 8 p.m. Good night.